the I hat part goes away. Is that sufficient?
Yes.
Jason?
When you have to FOIL, can you always get rid of the final times initial?
When you're
Like the whatever you said multiply, the C word, I can't remember what it was. Commonality,
commutative.
thank you.
Yeah, with
Is
dot
that
products,
always-
you can always commute.
You can always do that every
Yeah.
time, okay.
For those of you who remember it, this is very much related to if I have a squared minus b squared, that's equal to a minus b, a plus b, which is because the middle terms drop out with the FOIL. For those who don't remember it, just sort of log in the back of your head at some point later on, when you're on a game show, it'll come or when your kids ask about it, you go, yeah, I've done that. All right, what I'm gonna do now is I'm gonna distribute. I got this thing sticking out front and I got the stuff in parentheses here, so I'm gonna distribute. So I started out with total force. That was the total force times the displacement, which I called work, is the total work. It's going to be equal to 1/2 mv final squared plus 1/2 mv initial squared. Not plus there, that should be a minus. Now, obviously, 1/2 mv squared shows up twice. Physicists look at that and say, so much writing to do. Surely we can come up with something better. And they said, sure, let's do it. They use the letter K to equal 1/2 mv squared. Why are we using the K? Hopefully that will become clear in a moment. Unlike momentum, I do know this one. So therefore, my total work is going to be equal to this 1/2 mv squared final, so that's K final, minus K initial, which is just a change in K. Ooh, yeah, now it all becomes clear, right? Okay, let's fill in, maybe for a few of you, there's some gaps about why. First off, K is for kinetic. This is kinetic energy. Capital K is for kinetic energy. This formula, K equals 1/2 mv squared, I expect you to know. So if at any point I ask you, what is the formula for kinetic energy? In unison, the response is 1/2 mv squared. Don't embellish. Don't do 1/2 times the mass times the speed squared. Just 1/2 mv squared. And I am serious. Here we go. What is the formula for kinetic energy?
1/2 mv squared.
Chorus of angels that I like. This down here, where I have the total work is equal to the change in kinetic energy, this is known as the work energy theorem. Now, personally, I don't like the fact that it's called the theorem, because the reason why it's true is because we've defined work and we've defined kinetic energy so that it works. It's actually the work energy definition. However, I was not consulted. It is called the work energy theorem. Any questions before I erase? under certain situations, kinetic energy is conserved. Under certain situations, it's not. So the question is, when is it conserved, when is it not, or in general, when is energy conserved or not? All right, so I take a marker here. What is its kinetic energy?
0.
Right, it's not moving. I drop it. Is the kinetic energy does the kinetic energy stay the same?
No.
No, it goes from not moving to moving. Kinetic energy is the energy of speed. So physicists look at that and they go, wait a second, something's off there. We want a conservation law, so let's come up with one. They realize, what is the force acting on it as it falls?
9.8. I think.
We're in the ballpark now. What's the name of the force? All right, so what'd you say back there? The Kinsey? I thought I heard something.
gravity.
That's not the force. What's the force? Gravity, big topic. We'll look for.
Wait.
Yeah, there we go. That's good enough. Or force due to gravity. You said acceleration due to gravity. That's a different aspect. And they said, all right, so this work is causing, and so suppose we give that a label. There is a formal calculus-based definition. I'm not going to subject you to that. But they break forces up into two types of forces. One set are called conservative forces, and the other non-conservative. Crazy how they come up with these names. So these are the types of forces. Conservative forces, I think this might shock you, conservative forces will do conservative work. Yeah. Non-conservative forces, non-conservative work. It's crazy. Now, bypassing the formal definition of it, I'm going to list all of the forces that we have dealt with so far that are conservative. Done. That is the only conservative force we have dealt with up till now. We will deal with others. The non-conservative forces, tension, normal, friction. Friction's a classic non-conservative. So, write down the others. I think it's as simplest at this point, just to go with, let's just do the checklist. Conservative, weight is a gravitational force. It's a special case of gravitational force, so weight counts as conservative force. Now, another one that we will deal with is the ideal elastic force. And that's, and potentially electric force, magnetic force. That pretty much covers what we will do. The last two will hit in probably December. That is an E here. All right, but for right now, gravitational force is the only one. Why do you suppose it's called a conservative force?
It conserves energy.
Exactly. Non-conservative forces obviously don't conserve energy. So if I have non-conservative force, it's just going to do non-conservative work. Whatever the non-conservative work is, that's equal to the change in the energy. Now, I have two types of energy that I mentioned kinetic already. We have kinetic energy. The other type of energy, the one associated with conservative forces, is known as potential energy. For every conservative force, there is a potential energy formula. So if I ever ask you, what is the formula for potential energy? The correct response is, which one? All right, what's the formula for potential energy?
Which one?
That was not as chorusy of angels as the other one was. So if I'm talking about weight, the formula mgh plus a constant. If I'm talking about the generalized gravitational force, which we haven't really dealt with yet, it is big G, mass 1, mass 2 over r. M1 and M2 are the two masses attracted to each other. R is the distance between them. But I left there's a negative sign there I left off. Negative. Ideal elastic force, 1/2 little k delta x squared. Little k is known as the spring constant. It's basically how stiff. The larger this number is, the stiffer the spring is. Delta x is how far the spring has been displaced off of its natural hanging position. So if I took my slinky here, obviously not ideal, but good enough for now. That's its natural hanging position, if it would come to rest. And so from that point to, I pull it down a certain distance, the displacement from its natural hanging to where it is now, that's delta x. And I'll worry about those later. So I have the symbol for potential energy, as you would expect, is a capital U. I suspect it comes from the German, but I'm not 100% sure. So when we're talking about change in energy here, we have potential plus kinetic. So that's, so my total work, total non-conservative work, is equal to the change in potential energy plus the change in kinetic energy. Yes, I'm sneaking in another derivation right now. Change in kinetic energy, I know, is equal to the total work. So this is the change in potential energy plus the total work. And my total work deals with the total force, which means all my conservatives plus non-conservatives, it's the whole thing. So my total work is just conservative work plus my non-conservative work, because those are my only two choices. So I have non-conservative work is equal to delta U plus my conservative work plus non-conservative work. That's just my total. Non-conservative work cancels out. And that is supposed to be an equal sign in between. And if I subtract delta U from each side, I end up with the whole point of this. I have the total work is equal to the change in kinetic energy. That's the work energy theorem. I have the non-conservative work is equal to the change in energy. And I have the conservative work is equal to the negative change in potential energy. These are the work energy equations or work energy relationships. And we will exploit them as we go. Yes?
See what's after the half?
That's a K. I tried to make a sort of a fancy lowercase k. And then delta x squared. Now there is something I left off of two of these. I remembered to put the plus c there, plus c, plus c. In essence, it's just a constant, c for constant. For any of these formulas, I can always add a constant to it and not change anything. Because what really matters is the change in potential energy, not the actual value itself. All right, questions here? Yes, Johnny.
What's the little symbol on the first one?
That?
Yeah, that.
That's TOT for total.
T and T?
TOT, total. Sometimes I'll do net instead, the net work, which is the same as the total work. Which is the same as the sum of all the works. I have a 5 kilogram rock that is going to fall. Let's say it starts out at an initial height of 30 meters. It's going to fall till it's 10 meters above the ground. And I want to figure out how fast is it going when it gets to here. Assume that the initial speed is 0 meters per second. And I want to find the final speed. I can solve it 2 different ways. I can solve it using the stuff we did in chapter 3. And now I can solve it using the energy stuff. So let's start do the chapter 3 way first, and then we will do the chapter 7 way. There we go. All right, so I have an object, the initial speed is 0. Since I'm just dropping it, then I know that the distance it falls is going to be 1/2 GT squared. I know that that is, well, how far is it going to fall? 20. So I got 20 meters equal to 1/2, and let's just simplify this to 10 meters per second squared. Earth 2 times time. So I have 20 is equal to 5t squared, divided by 5, divided by 5. T squared is equal to 4, t equals 2 seconds. It takes 2 seconds for it to fall. How fast is it going when it gets after those 2 seconds? Well, I know after 1 second it's going 10 meters per second. After 2 seconds it's going 20 meters per second. The acceleration 10 meters per second squared means the velocity will change by 10 meters per second each second. Or using the Hewitt equation, V equals GT. This is for an object that is dropped. So that's 10 times 2, 20 meters per second. Chapter 3 approach. Chapter 7 approach. What are all the forces acting on the rock as it falls? Okay. Everyone catch that? Is that a conservative force or a non-conservative force? It's conservative. All right, so if I look at that, the second equation over there, that work non-conservative equals the change in energy. Well, my non-conservative work is 0 because the only force acting on it is conservative. So that's equal to my final energy minus my initial energy. I'm just going to bring that energy over to the other side. So I've got my initial energy equals my final energy. That is just the sum of it. That is the shorthand notation for saying energy is conserved. Whatever total energy I have at the beginning, I've got at the end. I got 2 types of energy. What are they? Yep. I got some initial kinetic plus some initial potential is equal to my final kinetic plus my final potential. I'll have to ask that question again. what is the formula for kinetic energy? That was sad. We can do better. I believe in you. I heard you do better. Here we go again. What's the formula for kinetic energy? There are a couple of people whose mouths doing great ventriloquist act or did not answer. Yeah, I was looking at you, Kenzie.
Me? I didn't.
If you said it, it was,
Wrong.
yeah, didn't see the mouth move. All right, so we got 1/2 NV initial squared plus, what's the formula for potential energy?
Which one?
That's the right question. The one associated with the conservative force here, which is weight. What is the formula for the potential energy associated with weight? It was written over there, but, yes. All right. mgh plus some constant is equal to, that's initial, is equal to 1/2 NV final squared plus mgh final plus some constant. Now, the reason why the constant usually is not mentioned in textbooks is that, well, it's gonna cancel out. Whatever the constant is, it goes away. So now the question is, can we get rid of, are any of these things equal to 0? Is the initial speed 0?
Yes.
Okay, thank you. So that whole term goes to 0 because the initial speed is 0. Is the initial height 0?
No.
Okay, you're shaking your head no, right? All right, so that still stays. Is the final speed 0?
No.
Is the final height 0?
No.
Okay, so we're left with this. Now, I do have mass in every single term. I could cancel it out, or I could just leave it there and just plug the 5 in. The 5 in. Either way, well, we can plug the 5 in. So I've got 5 times 10 times my initial height of 30